Hello again. So I'm using Screencastify and I have a time limit of 15 minutes for each post. So this will be in 15-minute segments. We just finished our definition of longitudinal waves. And in a longitudinal wave or compression wave, the medium oscillates parallel to the direction of the wave shape velocity. So an example of a compression or longitudinal wave would be sound waves. The air compresses and then expands in successive vibrations. The traveling of the compression is in the same direction of the oscillation of any particular particle of air in the wave. A longitudinal wave doesn't look like a sinusoidal wave. It looks like portions that are more dense, less dense, more dense, less dense. But if I were to graph density versus position, I would see high density, equilibrium density, low density, equilibrium density, high density, equilibrium density. And if the source of that compression wave is simple harmonic motion, then the shape of the density versus position graph will be sinusoidal, just as the shape of a transverse wave will be sinusoidal if the oscillation that starts that wave or that forms that wave is itself simple harmonic motion. It's easier to see the simple harmonic motion, or it's easier to see the sinusoidal nature in a transverse wave than in a longitudinal wave, but a longitudinal wave still does have amplitude, wavelength, and all of the other features. It's just only apparent in a graph of density. So the amplitude is the amount of compression from equilibrium or the amount of expansion from equilibrium. The wavelength is the distance from maximum compression to the next maximum compression, or maximum expansion to the next maximum expansion. So in a classroom lecture, I would then have a slinky and ask you to make a transverse wave and a longitudinal wave with the slinky, but obviously that's not happening here. Ooh, I will say though that in the module for waves, I've posted some simulations that you can mess around with for waves that may be quite useful. Okay, so does a longitudinal wave, such as a sound wave, have an amplitude? Since I just talked about this, I hope you answered yes. The amplitude is measured as the amount of compression or expansion, the difference in density from equilibrium as the wave passes. At a football game, the wave might circulate through the stands. In this wave motion, people stand up and sit down as the wave passes. So consider the medium to be the people's bodies. What type of wave would this be? I hope you answered transverse. The wave moves, let's say you're looking at the stands from left to right, and as the wave crest moves from left to right, the people, the particles, are oscillating vertically up and down. So that's perpendicular to the direction of the wave crest motion, which is the definition for transverse wave. And then the follow-up is what type of wave occurs when you toss a pebble in a pond? If you kind of the key is, do you see a sinusoidal shape? And the answer is on the surface of the water, yes, you do. So transverse wave. So speed in a medium. We've talked about wave speed. Our definition for velocity, distance per time, led us to the wave speed equation. Wave speed is wavelength divided by period. But the wavelength is determined by the medium itself. The period is determined by the frequency of the oscillation that causes the wave. How far the wave can get in the medium it shows up in the wavelength, but the frequency is fixed. The frequency has to do with how quickly you shake the string or how quickly you splash the water with your fist, and so on. So wave speed is proportional to wavelength and frequency. However, the wave speed is not determined by wavelength or frequency. Instead, the wave speed is determined by the medium properties. So the velocity is determined by properties of the medium. I think I've misspelled some things here. But you cannot change the velocity of a wave unless you change the medium through which it travels. So for a transverse wave on a string or something similar, the wave speed, and this equation on the left of your screen here, is equal to the square root of the tension in the string or cord, whatever it is that the wave is passing through, divided by the mass density of the string or cord. So you can kind of imagine it as a slinky. If I have a particular slinky stretched out across the ground, and I shake that slinky, if I shake it slowly, I'm going to get a wave shape that looks something like this. If I shake it more quickly, I'm going to get a wave shape that looks something like this. But the ratio of wavelength to frequency, so the distance between trough or peaks and the amount, or rather the time it takes for a peak to pass, or we could say the frequency, the number of waves per second, those two things change in tandem with each other. It's only if I stretch that slinky more tightly, so if I tighten up the slinky, I will change the speed, or if instead of playing with a metal slinky, if I switch to a plastic slinky, will I change the speed? So it depends on the tension. A higher tension gives you a faster wave speed. That makes sense because with a higher tension, you have kind of a snappier response to your medium. And then a larger mass density gives you a slower wave speed, which also kind of makes sense. If I have more mass per length of my string, it's going to be more resistant. The string itself will be more resistant to changes in motion. It will have more inertia. So it'll be sluggish in response to the passing energy of the wave form. So as I mentioned before, sound waves are longitudinal waves. And here's an example of a drum producing a sound wave. When a drum produces a sound wave, the skin, the sort of surface of the top of the drum, oscillates forward and backward. The same thing happens when a speaker produces a sound. So when the drum membrane oscillates or pushes forward into the air, it compresses the air. That compression moves on to the right, and the drum membrane in turn, what do I want to say, like bends back inside of the drum, at least a little bit. And so in bending back inside of the drum, the air nearby gets expanded. That expansion moves on to the right as the drum membrane pushes out again, and it happens in successive compressions and expansions, creating this ongoing longitudinal or compression wave. I'm honestly not sure why that slide is there. It should have been back with the longitudinal versus transverse definition. All right, so a wave pulse can be sent down a rope by jerking sharply on the free end. If the tension in the rope is increased, how will that affect the speed of the wave? I hope you answered that the speed of the wave increases. Increasing the tension, according to our wave speed equation and kind of thought process about the workings there, should show you that the speed increases. Okay, a wave pulse is sent down a rope of a certain thickness and a certain tension. A second rope made of the same material is twice as thick, but is held at the same tension. How will the wave speed change as the wave moves into the second rope? I hope you answered that speed will decrease. So if you have a thicker rope of the same material, you've increased the linear density. You've shoved more stuff per meter or whatever of rope. And so your wave energy now has to oscillate more mass as it passes a point in space. That more mass has more inertia to the change in motion sort of required by the passing energy. Okay, now there's a question like this, similar to this at least, similar line of reasoning on the 2018, I think, AP Physics test about where the string is moving, when it's accelerating, particles of string versus